Hello, I'm Mr. McBrien. This is SCH4U, Collision Theory and Rate Law. So the Ontario curriculum has a lot to say about collision theory. They would like for us to be able to talk about collision theory in terms of potential energy diagrams and in terms of the factors that affect the rate of a chemical reaction. So we're going to talk about some of that today. So our objectives, we want to be able to define the reaction mechanism for a given reaction, discuss the rate limiting step in a reaction mechanism, determine the rate equation from a mechanism, and be able to determine the rate equation from experimental data. Lots to cover today. So yesterday we talked about the factors affecting rate. We talked about temperature, surface area, concentration, reaction type, and catalysts. Today we're going to focus on a couple of ideas. We're going to expand on what we discussed yesterday with regards to temperature, and then we're going to dig deeper into the concept of concentration. So we need to be able to discuss collision theory in some detail if we're going to talk about reactions intelligently. So we go back to this concept of heat again. Particles have kinetic energy. Their average kinetic energy is proportional to their temperature. Chemical reactions must involve collisions of particles. Particles have to be close together before they can react. Now, if we combine these ideas together with the concept that collisions have to be effective before a reaction can occur. In other words, we have to have correct orientation and sufficient energy to overcome what we call activation energy, something we'll talk about in a few seconds. We get to this idea that the rate is equal to the frequency of collisions. In other words, the number of collisions per second, per minute, what have you, times the fraction of collisions that are actually effective. And this gives us a key concept to move forward. So before we go any further, we need to talk about something called activation energy. Now, activation energy is the minimum energy with which particles must collide before they can rearrange in structure. Now that rearrangement takes the form of what's called an activated complex. It's a temporary arrangement of reactant particles that contains partially formed and broken bonds, and we sometimes call this the transition state. So this is typically a short-lived beast. Now, this is entirely consistent with our ideas of energy of reaction, and in fact we're going to bring up some diagrams we've already shown before. So if we want to take an endothermic reaction, let's call this a forward direction reaction. So it's a reaction in which we must put in heat, so the energy of the reactant starts low, the energy of the products is something higher, so we have to put energy in. Now, we might think that the amount of energy is just this amount that is absorbed, and that as long as our kinetic energy of our particles when they collide is greater than this energy that needs to be absorbed, things are going to go fine. But in fact, this isn't the case. What generally happens is that the energy of the reactants goes through a higher energy situation where the energy level is higher than the reactants or the products. And this energy difference between this temporary state here and our starting point is called the activation energy. And what's interesting is if we take the reaction in reverse, going from those products and going back to the starting state, we'll typically go through a very similar or identical transition state. In other words, there's an activation energy for this exothermic reaction as well. But typically this activation energy will be a little less because the reactants are higher energy to start with. So in both cases, though, these reactions will go through an activated complex. And this activated complex that is in between reactants and products, well, the energy required to get to this point, we call it the activation energy. And it's this activation energy that determines the kinetic energy that must be present in the collision that occurs. So, if we keep in mind then our reaction and our transition state, before the reaction can proceed, the transition state has to be achieved. This needs the energy that we talked about, the activation energy, but it also typically requires orientation. And we'll talk about both of these. So the collision energy, as we mentioned, when a collision occurs, it has to have enough kinetic energy to generate the transition state. This is to overcome the activation energy. The more kinetic energy in the particles, the more chance the collision is going to provide that energy. So this is a little bit of a busy picture here. But in red, we have a histogram with the number of molecules possessing a given amount of energy. This blue line denotes the activation energy, the energy that's required to have a productive collision. And we can see that only the molecules to the right of that line will have enough energy to react. Any of the ones below that don't have enough energy. Now in purple, we have a higher temperature sample. What happens is this histogram shifts to the right, and more of these molecules have the energy necessary for the reaction. So it's this shifting of this bell-shaped curve to the right that produces more molecules with the energy necessary and increases the rate of reaction. Now, we might say, okay, so all we have to do is heat up the sample very hot and reactions will go extremely quickly. And this is, to an extent, true. However, not every collision will still result in a reaction. Now here's why. If we take the example of carbon monoxide reacting with oxygen to generate carbon dioxide, we can have collisions where the oxygen molecule comes in contact with the oxygen the oxygen side of the carbon monoxide molecule, and regardless of the energy level, no reaction is going to occur. It simply can't produce the transition state that we need. In contrast, if the oxygen comes in contact with the carbon side of the carbon monoxide molecule, well, then we have a situation where we can generate our transition state, we can have a reaction, and carbon dioxide can be generated. So it's another thing to keep in mind is that collision geometry is a consideration regardless of the temperature of the sample. Now all of this takes us to this idea of a reaction mechanism. So far, almost exclusively, all that we have talked about in our chemistry careers is balanced chemical equations, and we've put a lot of value on that balanced equation. Only in organic did we a couple of times start to talk about what occurs when we have that arrow that says a reaction occurs. In fact, there can be much more complicated things going on than simply one molecule transitions into another. Reaction mechanisms can be a series of elementary steps that combine to make our overall balanced reaction. Now, you might say, okay, well, but who cares? And to a certain extent, it's not important until we start trying to understand the energetics of reactions and controlling the rates of reactions and things like this. Then it can become very important what those steps are. So the most obvious thing that the most obvious benefit to understanding the reaction mechanism is that we can identify in these elementary steps whether certain steps are much slower than the other ones. If they are, we call these the rate determining step, and they're extremely important to the rest of the reaction. And it is these rate determining steps that become the most significant aspect of our reaction progress diagram. And we'll get to there in a few seconds. Now, we've already talked about the idea that the rate of a reaction is proportional to the concentration of reactants. And this is true, but it isn't the whole story. In fact, it's a great simplification, and we're going to abandon that simple idea and start to dig a bit deeper right now. Why? The answer is because some reactants are much more important to the rate than others. So our rate equation, if we take a given reaction, if we take the reaction of X and Y with the stoichiometric terms of A and B, moving to some products, the rate equation can be written as the rate is equal to some constant times the concentration of X to an exponent times the concentration of Y to an exponent. And the obvious question that comes up right away is, well, yeah, but what are the values for M and N? And in fact, that's the subject of the rest of our discussion today. Now, to illustrate this idea, let's take a multi-step reaction. So we're going to dig deep now into a reaction mechanism. So our multi-step reaction is this: hydrogen bromide reacting with oxygen to form this guy that I'm not even going to try to name. That intermediate reacts with another molecule of hydrogen bromide to form another intermediate. Two of those intermediate molecules react with two more hydrogen bromides to form water and two bromine gas molecules. Now, these are three steps in one overall reaction. And I didn't mention what was over on the right. As it turns out, if we peer into this reaction a little more carefully, we will see that this first step is an extremely slow reaction. And the other two reactions of these intermediates are actually quite fast. So let's keep that in mind. We'll shelve that for a second. And first, we're going to decide to look at our overall reaction. So what we're going to do is we're going to cancel and add together. We've done this kind of thing before. So we're looking for anything we can find on both on the left and the right-hand side. So this crazy intermediate goes away. These two intermediate molecules also go away. And now we're left with our overall reaction. 4 hydrogen bromide on the left, 1 oxygen on the left, 2 waters on the right, and 2 bromine gas molecules on the right. This is our overall reaction then. Now, what's interesting here is that once we know our reaction mechanism and we can identify the slowest step in this, we know the exponents in our rate equation. We can look at the reactants in the slow step, look for the exponents here, or the coefficients here. In this case, both are 1. And this gives us our exponents in our rate equation. So the rate here is a constant times the concentration of hydrogen bromide times the concentration of oxygen. So this is our rate equation based on the reaction mechanism. And if we go back to our potential energy diagram, what we'll find is our three reactions are all reflected in this potential energy diagram. However, our first step, that initial rate limiting step, that slow step, has the highest activation energy. Once that intermediate has been formed, notice it's this guy here. Once it's been formed, the rest of the equation proceeds very fast. You might look at it as once you're at the top of this mountain, everything else is downhill. So the other two transition states are achieved very quickly once we've gotten to this point. So what this means is that anytime we have the reaction mechanism, we should be able to define the rate equation very quickly by just simply transcribing the stoichiometry numbers into the exponents for the equation. Well, what happens if we don't know the mechanism? And in fact, this is the more common situation. When we discover a reaction, we rarely know the mechanism right off. In fact, one of the key clues that helps us determine the reaction mechanism for a given reaction is careful observation of the kinetics involved. In other words, we figure out the rate equation first to help us determine the reaction mechanism. So how do we do this? We do it with systematic design of experiments. We measure the rate as we change the concentrations. And experimentally then we can determine the rate equation for our given reactions. So let's look at an example. Let's say we're studying the reaction of nitrogen monoxide with hydrogen gas to form nitrogen gas plus water. And let's say we double the concentration of nitrogen monoxide and the rate quadruples. It goes up 4 times. Well, then we ask ourselves, what's the coefficient for NO? What's the exponent for NO? Well, the answer, of course, would be it's a square term. We doubled it and it went up by 4. Now let's say we triple the concentration of hydrogen gas and the rate triples. Well, the exponent there is clearly a 1. So this gives us a rate equation then. The rate is equal to K times the concentration of NO squared times the concentration of hydrogen. So you might ask yourself, okay, well, can the rate ever be independent of the concentration of a reagent? And the answer is yes. In some cases, one or more reagent may not be part of the rate limiting step. And if it's not, then what we're going to see is that provided our reagent is present, its concentration isn't going to impact the rate. And that may seem counterintuitive, but it's the truth. We can double the amount of that reagent and it won't increase the rate appreciably. And the reason why is because it's not involved in the rate limiting step. Now, all of this just corresponds to the idea that M or N is able to be equal to 0. So it's perfectly acceptable for M or N to be equal to 0 in our rate equation. And once that happens, remember any number to the exponent of 0 is equal to 1. All right, to summarize, collision theory explains many aspects of rates of reaction. If we make a change to our reaction mixture that will result in more and faster collisions, we should see an increase in the rate of reaction. Rate equations get expressed in terms of concentration of the reagents in the overall reaction. The exponents, however, are determined by the coefficients of the slowest step in the reaction mechanism, the rate determining step. Okay, so for the homework, please read over the notes, and we've got 2 worksheets for today because we've got lots of great concepts to work through. Thanks very much, and have a great night.